All right. Good morning to all of you who made it here early by at least 5 minutes. So good job there. Um, uh, so you can see my mind map, which is I find this to be a quite useful way to kind of plan the class for the day. Obviously, this is not officially a part of the lecture, so but for people who got here early, I can share this with you. Oh, that's all right. Not a problem. Let me unmute on the server. There we go. So now, Daria, you can mute yourself. Your mic is still on. Okay, there we go. Thank you. All right, so what we'll be doing today is we'll revisit some of the stuff that we talked about already, starting with negative exponent. Well, to be more exact, it is negative exponent of 10. So we want to get that to 0. And then the next thing we want to do is to revisit the NAND gate. It's just going to be a really quick one. And then we'll talk a little bit about, well, these are the things that we have talked about already, but that those are needed in order to get to the future stuff. Exam 1 is being graded, so anyone who want to ask about exam 1, I spent Saturday, Sunday, and Monday for the most part, grading exam 1, and it was slow. And that's because I was reading every line of reasoning, every link of reasoning when people try to figure out the bits. So that took a little bit of time. Um, and you are already sent a link with your own exam answers and also the key to the exam. The way I share that back with you is you are a commenter, which basically means you can leave behind comments. Unfortunately, Google Doc also allow people to make suggested changes to the document when they are commenters. And that was not the intention. I got one person who was trying to put in all the correct answers after the fact, and I really do not know why that person was doing that. But anyway, I was able to undo all the changes and change that person from commenter back to a viewer, so that no other further suggested changes can be made. So that was that. They're being graded. They're being graded. I think I got maybe a third of the class graded. It was really slow. I mean, I could grade like maybe 2 or 3 exams per hour. Yeah, well, it took you guys what 80 minutes, to do one, and I have to follow the same reasoning. I have to read every single line, every single character, every single implication to grade it, to basically say, okay, does that make sense? Does that make sense? Does that make sense? So it's taking a little bit longer than I expected, but it is worth the time because now I get to understand, what people understand, what people do not understand, and so on. And I'll be able to, and I was able to differentiate the varying level of understanding of the material because of the answers. So that's illuminating in a certain way. And as I said, this is the first time I basically just reuse all the same type of questions as a previous semester. I cannot say I reuse all the questions because I mean, I'm suspecting no 2 people in the class, had exactly the same question. But other than that, it's interesting. Okay, it did not really change the grade distribution as far as I can see at this point compared to when this kind of exam was first introduced. So that should answer Lisa's question. And when I grade, I only see the student ID, and I don't remember the student ID of anyone in this class except that of myself. So, there's definitely no names involved when I grade the exams. So this is how I try to make sure that I try to be absolutely fair, because I really have no idea who is who when I grade the exams. All right. And we got a minute left. So what we'll do today at least at the beginning, is going to talk about how to handle the positive exponent, and you're going to get this lab also released today. Once you have started to work on the negative exponent, the positive exponent is very, very close in terms of the logic. It's just kind of the opposite. So we'll talk about that a little bit. And then we're going to move on today to SR latch, okay, which is basically the smallest unit of how we can remember bits inside a computer. So that's kind of what we're going to do today. And we got about 10 seconds to go before the class starts. And I got a question coming. Okay, how is everyone doing on the negative exponent lab so far? Some people have turned it in already. The setup can be a pain. If you use online GDB, it's not. I mean, you just download the monolithic version, and I might have posted the corrected version too on Discord. So you just you upload the whole thing and you copy and paste it. And I would also suggest, if people are using online GDB, sign in first, because if you sign in, you can actually save the file remotely because it's all in the cloud. So you can basically do this assignment completely using a Chromebook, which is kind of cool in a way. All right, so Terrence is asking, so where are we in terms of the notes module? Should we start on D flip-flop? Yes. So that's going to be the next one. We're going to start in it today, actually. And Jonathan said VS Code just failed and CodeBlocks isn't really supported on Mac OS X for some reason. Well, I can tell you what the reason is. It's an Apple product. If it's not coming from Apple, it's not going to be well supported. In fact, Apple may just say, no, we're not going to let you install this because it is not from us. I really like Apple hardware. I just cannot handle how they police and restrict what I can do on my own computer that I pay for. So that's something that I do. Yeah, online GDB is really great. And I use it in class too. So you can basically just replicate what I did in class to set up the whole thing. The only thing is when you run it in the GDB, you have to R space and then -n and then a space and then whatever number you want to use to test your code. Yeah, Xcode works on Mac OS, and online GDB is, yeah, I would just highly suggest online GDB for all practical purposes. Yeah, Apple is a really tough walled-in garden. I think they call that garden in a prison with watchtowers and barbed wires to prevent other people from getting into the garden. Yeah, that would be a good idea, to standardize charging cords and stuff. So I use a Lenovo, and I use Linux on top of Lenovo. Works great. I mean, the combination is great. So anyway, let's get the class started. So we are going to start with how do we handle a negative exponent of 10. Excuse me, take it back. How do we handle a positive exponent of 10, and how do we decrement it? So let's go ahead and get started with this. And I might even just try to do this, using free plane. Okay, so just brain fart right there. You cannot remember the word. Okay, there we go. And we are going to reintroduce, okay, what is the value, okay, because some people ask me, how do I check my answer for the the current assignment? So the idea is the value being represented is always the same. V is always the same. The question is, how do we represent it? So I'm using M to represent mantissa here, and it's not strictly the mantissa, because the mantissa has to be normalized, which means it has to be a value that is greater than or equal to 1, but less than whatever base we choose to use. So the mantissa that I refer to in this context is merely just a quantity that we multiply to the other two quantities that we'll be talking about. So the mantissa is a 64-bit unsigned integer, um, and then we want to multiply that. Okay, so we want to use a C dot for multiplication. So the next component that we multiply is merely just 10 to the power of I'll call it E10, which is the exponent of 10. And then that in return is also multiplied to 2 to the power of E2, which is the exponent of 2. So that is always the value being represented. Let me bump up the zoom ratio so you guys can all see this a little better. There we go. So the V would never change. Okay, V should be remaining the same as much as possible. Because when we change the representation, we lose some ability to represent certain specific values exactly. But we will try our best to estimate it as much as possible. So when E10 is positive to begin with, we want to be able to decrement it, right? So we want to be able to decrease E10, which is basically just an integer, one at a time. So if we started out with 99, okay, we wanted to turn it into 98, and then 97, and then 96, and so on. So the question is, how can we do that? So the math, that works out in this case. Okay, let me see, why is it not doing that? Interesting. My Spotify is automatically paused because Discord decides that when I'm live streaming, it would turn off Spotify, which is not really what I want. I want it to keep playing, and doesn't seem like there's an option to do it. That is interesting. I didn't know that. Because I made sure that you guys cannot hear what I'm listening to, and so it's just a little bit of background music to me. Anyway, it's not important. And oh, okay, I see. Yeah, that's kind of a problem. It's okay, not a problem. There we go. So what we want to do is to copy this, and then we'll go ahead and say, what can we do to change this whole thing? So let me do Control A, Control C, and then there has to be a way to duplicate a cell in FreePlane, but I'm not going to do that. I'm just going to repaste the whole thing here. All right, so what we're going to do is to say I want to decrease the exponent of 10 by 1, so I want to subtract 1 from here. But if I subtract 1 from here, that means I have to multiply the mantissa by 10. Okay, so I'm going to do this first, and then when I press the enter key, it will become more clear what this is representing. So that's what we want to do. So by multiplying the mantissa by 10, I can now decrease 1 from E10. So you can kind of imagine that in this case, imagine this is not M times 10, it is M times equal to 10, which means I'm changing the mantissa to be 10 times what it used to be. And instead of E10 minus 1, it is E10 minus minus. I'm decrementing E10. So this approach sounds great, right? It sounds great when E10 is reasonably large. So for any E10 that is up to 18, we can do okay, because that's within the range of a 64-bit unsigned integer, and we already talked about how to find the range of an unsigned 64-bit integer already, so I'm not going to talk about that again. But the point is, what if E10 is more than 18? Okay, if it's 19, 20, and so on, then we're going to be out of the range of an unsigned 64-bit number. So what are we going to do? In other words, what if E10 is 99? Okay, that for sure is going to be exceeding the range. So what are we going to do? I'm going to let you guys think about it a little bit. I mean, the the answer is staring at you on the screen right now. So, but I do want you to kind of absorb that a little bit and think about it a little bit here. Yep. So Terence is correct. So what we want to do is to, when m is quote unquote out of room to multiply by 10, we're going to divide it by 2. And if that is still out of room, we'll divide it by 10 again, excuse me, by 2 again. And we'll keep doing that until there is room for another multiplication by 10. Okay, so it's kind of the reverse of what we are currently doing with the negative exponent assignment, except in this case, we want to make room by dividing m by 2 until we have room to multiply it by 10 again. So now the question is, when do we stop? Okay, so I'm gonna put my notes here. So the question is, when do we stop, quote unquote, making room in the mantissa? Okay, what is that condition going to look like? What do you think? Okay, when do we run up, against that limit? So the equation, or the most intuitive way to look at the equation is, if we multiply m by 10 again, it is going to exceed what we can represent using an unsigned 64-bit integer. So we'll say, if we multiply that by 10 again, it's going to be greater than u int 64 underscore max. And yes, you are correct that I'm giving you part of the answer because I need to use math. I think TT would work here because I need it to stand out a little bit. Yeah, that works. Okay, except the underscore is interpreted as subscript. There we go. So a backslash in front of it should escape it. There we go. All right, except this approach doesn't work. If it's greater than 18. Well, you can rest assured that when I test your code, I'm going to use an exponent of 10 that is greater than 18. So the question is, how do you deal with it? Okay, and Richard is correct. Okay, because when you work out this math here, you just have to do your algebra to find out how you can compare m on only one side. There's only one term on one side, which is m, and then the rest of the stuff, the constant stuff, goes on to the other side. Okay. Except there's one a little bit of an issue here, because when we divide by 2, we have to add 1 first, right? So we have to kind of make sure that when we add 1 to whatever m is, that does not exceed the range either. So so you kind of have to take into that consideration. It's not really that big of a deal, because it's a very small amount, and I think it's almost impossible to hit that boundary case. Why is that? Define that. I think that probably is the reason, right? Because we have to use rounding. Every time we divide something, we have to use rounding, because if we don't do rounding when we divide, then we end up with a biased error. It is always going to be smaller than what it is supposed to be. So we have to do rounding. So we talked about rounding in negative exponent when we need to divide by 10, and the general approach is also in the module, because we have to basically add 1/2 of the denominator to the numerator before we perform the division. That is going to perform exactly the same thing as rounding, but using only integer division. So there we go. So we have to make sure that after we multiply m by 10 and add 1 to it, it will still have room. But that is really not an issue, because 10 has 2 in it, right? Because 10 is 2 times 5. So when we multiply m by 10, we are guaranteed that it's going to be an even number. And uin64 underscore max is always going to be an odd number. Okay, so let's check that. Okay, how do we know that uin64 underscore max is always an odd number? I want you guys to think about it. What does it look like in base 2? Exactly. So it's 2 to the power of n minus 1. Now, 2 to the power of n is not always going to be an even number because 2 to the power of 0 is 1. But that's the only one where it is not an even number. Okay, so if n is greater than 0, then 2 to the power of n is guaranteed, guess what? An even number. And when you subtract 1 from an even number, what do you get? An odd number, right? So because m times 10 is guaranteed to be an even number, so when we add 1 to it, there's no way that it can exceed uin64 underscore max at all. Okay, there's absolutely no way for that to happen. And then Jonathan wrote n mod 2 is 0. Since we subtract 1, it has to be odd. Exactly. So I'm not concerned about that, one little extra one, plus 1, but you have to remember to use rounding instead of flooring when you're looking at the result of the division by 2. I'm not going to give you the equation because this has been mentioned in the lab. You should be using it in the negative exponent program already, at least the approach. So this is just another instance where you have to remember to use rounding instead of flooring. We have to adjust the EXP10 and EXP2. So I'm going to let you decide when to add 1 to which one and when to subtract 1 from which one. Okay. I mean, once you're done with the negative exponent, you would probably have a pretty good idea already how to do this. And I mentioned rounding already, so we don't need to mention this again. So I'm gonna take this note away. All right, so we got a text in. We're using rounding instead of flooring because we're supposed to only use integer math. That is correct. There should be no double whatsoever in the program. There should be no reliance on double or float in the entire program. No exponent, no power, no round, no floor, and so on and so forth. So if I see a program using those things, I'm just going to say, I told you already, don't do that. All right. All right. Well, somebody just gave us part of the answer to this particular thing. So, now these are bits and pieces, right? So you still need to understand, how to put the whole thing together, the big picture, to put it together. But let's not try to put too much of the answer into the text channel, shall we? All right. So I think that's that. Okay, we are now done with the next assignment, which is going to be assigned today. It's already assigned today, I should say. It's already assigned today. It is positive exponent. So we have 2 programs overlapping. Now you can put both into the same code. Okay, the first, when you submit it to negative exponent, I will only test it with a negative exponent of 10. Okay, so no need to worry that your code for positive exponent is not quite done yet. It does have to compile. Okay, any program that does not compile will get, guess what, how many points? This many. 0 points for anything that does not compile. Anything that crashes when it runs would also get, guess what, 0 points. There's absolutely no reason for any program not to compile or not to run or crashes when it does run. Okay, we are not using pointers. We are not, this is not recursive, although you can make it recursive if you want to, but there's no reason for a program to crash. There's no reason for a program not to compile. So any answer that, does not compile or crashes, when it runs, is going to get this many points. Yes, I am using GCC to compile, so you probably want to make sure whatever compiler you're using on your side is compatible with GCC. I don't think you need to use anything that is tricky or specific to, particular versions of compilers that are not GCC. So I really think that that should not be a big concern. All right. And we still got one person typing. And I'm going to wait for that before I start to talk about the concept of an SR latch. GCC? Well, GCC is what online GDB uses. And also, if you use the default version of code blocks, it also uses GCC, which stands for GNU C compiler. And then GNU itself, GNU, stands for GNU is not Unix. It is a infinite recursive definition. And people like that, at least back in a certain time. So I'm gonna type in the text channel because some people may not have caught that. So it's the GNU C compiler, and GNU means GNU is not Unix. There we go. Yes. All right. So we can go ahead and answer one question. So I'm not sure which one people want me to talk about in binary subtraction. As an example, all right. So I got a question. All right. So let me see if I can do this. I know I'm beating a dead horse here, but I think it is still kind of helpful to think about this. Okay, so I'm putting a problem in the text channel, and we'll try to solve that. Because, just in case anyone wants to find out, okay, how do we solve this, right? Okay, so let me see if it's even solvable, because if it is part of the question, it is going to be definitely solvable. But if it's not coming from one of the questions, it may not be solvable itself. So I'm going to switch to the tablet to do this. And I think it's still 3 by 3. I mean, I don't know for sure from this person, the person who asked the question, but I think it is 3 by 3. Let me check that. Yeah, it's 3 by 3. There we go. And my tablet is not cooperating. It won't stop screen sharing, and it thinks my tablet or my client doesn't have this feature enabled. All right, well, there are always other ways to do the same thing. I'm going to use mousepad to do this. There we go. All right, so we'll go ahead and open a new file. There we go. Okay. So y0 is a 0, t1 is a 1, t2 is a 0. So we know nothing about x. So x is going to be underscore, underscore, underscore. And then y has underscore, underscore, and then a 0. So that's the first two rows of the subtraction. And then this is the q row. Nothing is known about the q. Okay, so q are all unknown. And now we have the t row. So t2 is a 0, t3 is not known, this is known to be a 0, and then t1 is 1, and then t0 is unknown. And then we get to the d row, the difference, and nothing is known about the d row at all. And then we have overflow is unknown, and then the L flag is a 1. Okay, so those are the given bits. We have 4 given bits, and if this is quoted from the exam, it should be solvable. All right, so I know some of you are thinking, I'm really totally done with this kind of question. Can we just move on? Yes, after we revisit this one, okay? Because what is important here is the approach of solving the problem, not so much the knowledge. The knowledge you can just look up, but how you apply the knowledge to solve a problem, That is the general approach. So I always start with something that is known, right? Yeah, so L is known. There are a few bits that are known, and if you just look at, I'm just going to point out, this particular bit here, it's not going to give us a lot of clue as to what we can do. Actually, it does. I lied, because T1 being a 1. So the first thing you want to do is to basically be able to recite all the definitions. So T of I plus 1 is not xi. So I'm going to use the shorthand here without the square brackets. So not xi yi or qi not qi ti. All right. So what we know is T1 is a 1, which implies not xiyi. Oops, not. Let's not use I anymore because we know the index. So not x0 y0 or not q0 t0 is going to be a 1. And since y0 is a 0, not x0 y0 is going to be a 0. So T1 is a 1 because of not q0 t0, which means, okay, that implies not q0 t0 is a 1, which then further implies q0 is a 0 and t1 is a 1. Okay, so I got a few people typing in the text channel. I don't understand why Vlad thinks the T rule would say the Q0 is a 0. That's out of order. That is an out of order kind of reasoning. Yeah. And I misquoted here. So that's also one of the things that I checked when I grade the exam is out of order reasoning. How can you figure out this bit before that bit? It doesn't make sense, right? I mean, not in this instance, okay? But when I'm grading, when I see something out of order, I go like, that doesn't make sense. How can you figure out that, before that one? So those would get, they will get points deducted kind of big time. All right, so now we have figured out 2 bits. So we have figured out Q0 is a 0, and we have figured out T0 is a 1 here. So from there, we can basically work out column 0 entirely. So I'm going to say because y0 is a 0 and q0 is a 0, and x0 exclusive or y0 is q0, therefore x0 is a 0. So now I figure out one more bit. It's not really that useful because it doesn't lead to anything else. I just want to complete this column here. And we can also say because D0 is Q0 exclusive OR with T0, which in this case is 0 exclusive OR with 1, and that turns out to be 1. So now I can fill in this bit, and it is a 1. Okay, I'm getting back to so Vlad is incorrect because it is not a OR, it is an AND. Not Q0 and T0 is a 1. And that's why we can know for sure that Q0 has to be a 0, because otherwise the negation of that would not yield a 1 that we need in order for the conjunction to be a 1. Alright, so we got one column entirely figured out, and then we can look at this 0 here. This is actually telling us a lot too. So the T bits, the O bit, and to a certain extent the L bits, those are the very useful bits to know. So now we're going to use T2 being a 0 to say, okay, what can we tell from here? So T0 being at 0 means that not x1, y1, or not q1, t1 is a 0. So and since t1 is known to be a 1 at this point, so I'm looking at the order here because I figure out what is t1 from here. Okay, so I figure out what is t1 from, oh no, that's actually given. Never mind, brain fart, another brain fart. So since t1 is a 1, and we want not q1 t1 to be a 0, so that the OR between these two terms is a 0. So that means not Q1 has to be a 0, which then implies Q1 is a 1. Okay, so we now stash a 1 over here. All right, so we got a few text messages going on. Based on T1, not really sure what that means. T1 equals to not x0, y0, but it's not. It's not just that. It's the result of an OR. So T1 is T1 is this entire term. It's not just the first part. It is the entire OR. So when I see people quoting just one of the terms of an OR and say that T1 equals to not x0, y0, I also deduct points because that is not correct. All right. All right, so moving on. So now what do we do? Well, let's see here. We need this to be a 1. We need Q1 to be a 1. So Q1 is a 1. What does it imply? Well, one of two things, right? So it implies x1 is a 0 and y1 is a 1, or x1 is a 1 and y1 is a 0. That's what, because, okay, you guys can quote the letter of the rule, that makes it a little bit faster, but I'm just going to write this entirely here because Q1 is x1 exclusive OR with y1. Okay, that is the reason why we know it has to be one of these two. Okay, so it's either this one or this one here. But we know that we can rule out one. So this is the process of elimination. So in the process of elimination, we say if x1 equals to 0 and y1 equals to 1, then T2 would have been a 1, and this is a conflict. Okay, hence x1 equals to 1 and y1 equals to 0. So now we have just resolved. This has to be 1, this has to be a 0. So this is the kind of reasoning that I'm referring to that is important to answer this particular question. Now, how much detail, how many English words do I expect? Not really a whole lot. Just because I'm explaining this in class, I don't have a time constraint and I'm just going to type out as much as I can. There were a few people using a very shorthand thing, but it was complete. Okay, the implications, the quotes of the rules and the reasoning, they're all complete. I can see every single step of the reasoning, and they get perfect score. A few people put in something that is really terse and just completely not mention what bit should be what. Okay, and they just go like, they would conclude with this. Okay, I'll give you an example. So if someone just concludes with this without mentioning that Q0 is a 1 and T0 is, excuse me, the other way around, Q0 is a 0 and T0 is a 1, as a result, I'm going to take points off because it is not obvious. That step needs to be stated. Okay, all right, so moving on. So now we can also know what is Q1. So Q1 is, nope, not QD. D1 is Q1 exclusive OR with T1, which is in this case 1 exclusive OR with 1, which is a 0. So now I got this also resolved. All right, we got a few text going on. It has to do with the explanation. Okay, it has to do with the explanation. If the explanation is not sound, I'm gonna take points off. Now, I didn't quite pay attention to the text channel right now, but what I could see was using the wrong operator for sure. Okay, so when people use the wrong operator, I cannot give them all the points. All right, moving on. When do we get the results of the exam? When I'm done. I mean, I'm still grading it. I'm grading it as quickly as possible. I'm using the entire weekend and yesterday to grade it. So when it's done, it is done. I'm on it. That's all I can say. All right, getting back to here. All right, so now what do we do? Well, so out of all of these bits, L is going to be useful. So what we know is L is the sign flag exclusive OR with the O flag, and that turns out to be a 1 in this case. So what this implies is basically we can say there are two possibilities. The sign is a 1 and the O is a 0, or the sign is a 0 and the O is a 1. Okay, so these are the only two cases. Now we plug in both of these, okay, and see which one we can eliminate. Okay, remember the process of elimination. So that's what we're going to do here, is to eliminate one of them. So we'll say if, okay, I have no idea which one is which one, so I'm working this out as you are working this out. Okay, I don't actually have the key in front of me, nor do I want it. Okay, so if that is the case, what is the consequence of that? And I'm going to scroll off the screen, which is not helpful because that means I cannot look at the problem at the same time. So let me see if I can open the tab of the same document here. New window. Yeah, that might work. No, that doesn't work. Alright, so I'm not going to comment on your answers in the text channel because I'm actively trying to explain this to the class. So if you guys have any questions about your specific answer, you're gonna have to wait until this explanation is over and after the class is over. We can do it during the lab time. Right, okay, so I'm working on this one. So if the sign flag is a 1 and overflow is a 0, okay, so now we say sign is the same as D2. So if D2 is a 1 and T2 is a 0, then we know that Q2 is going to be a 1. Oh, okay, so I'm going to have to pause here because it's time to take roll. Alright, so let's take roll. Yeah, I know, I know you guys are thinking, what, are we kindergarten students taking roll? Unfortunately, if I don't take roll, a lot of people just simply do not show up. And from experience, from statistics, I know that when people stop showing up in lectures, they're not going to do well in this class. Not that that alone is a sufficient condition to do well in this class. I just know that when people stop showing up, usually it's downhill from there. Alright, so let me show you the answer first. And this one, I think you really want to just copy and paste. Oh, okay, I forgot to update it. This one is easy. Johnny. So this is derived from John von Neumann. Which is on the topic that we are going to talk about later today. So that is the answer. And let me save and publish. There we go. And double checking to make sure that you guys can access it. Yep. So you have until 9:46 to do it. Alright, so Ivan asks, do I encourage you to cover all the multiple possibilities? Sometimes I would choose a suitable possibility first. Try, well, if it does work out, it's okay. Okay, so because it's kind of known that only, okay, let me reverse. So it is known that there's only one solution to every single question. So if you work out one particular combination and it seems to work out, then it is the solution. So there's no need to use the process of elimination because you're guaranteed that there's only one unique solution to these problems. But I'm assuming that I do not know that, right? So I want to work out, all the possibilities, because if there are multiple possibilities that work out, then I should be able to choose one of the possibilities, and it should still be considered as the correct answer. All right. So getting back here, So now I know Q2 is a 1, and if Q2 is a 1, then we know x either x1, x2 equals to 0 and y2 equals to 1, or the other one, which is x2 equals to 1 and y2 equals to 0 in this case. So now we want to see if that is going to lead to problems. So I'm going to state here, if x2 is a 1, y2 is a 1, and the sign flag is also a 1, in this particular case, overflow is going to be a 1. In the other case, overflow is going to be a 0. So that works out, okay? So this case works out. x2 equals a 1, y2 equals a 0, and sign is a 1, and overflow is a 0. So we're going to plug in those values. So this goes back to what Ivan just mentioned about, oh, okay, on first try, I got the one that works out. So this is a 0. This is going to be a 1. Oh, it's not going to work out, is it? Let's see. No, it does work out. Okay. So the other one does not work out in this case. So if I were to assume the sign is a 0 and overflow is a 1, that is not going to work out. That one will lead to a contradiction. All right, so now we got almost everything worked out except for T3. So T3 is not x2, y2, or not q to t2, which in this case is a 1 because we know all of those bits already. And overflow, we also know is going to be a 0 in this case. So now we have resolved the very last one here, which is a 0. And this entire thing is done. Okay, I just said it's supposed to be a 0. My mistake. All right. To address Vlad's concern, because I would need to know how you guys solve the problem, so it is important for you to show me the steps. Okay, so there's no way around that one. I have to look at how people solve the problem, and the reasoning has to be sound in order to get the points. All right, so I'm not gonna address specific questions in the test on for individuals. I'm going to grade it. Once you get it back, you can kind of ask me why points were deducted. I try my best to put in the comments. I'm doing everything on my tablet, so I'm leaving behind like tons of comments. It's kind of like grading an English paper, except it's not English. All right, so Jonathan is asking, why isn't x2 being 1 and y2 being 1? Because if x2 is 1, y2 is 1, then we end up with a 0 here. 0 minus 0 is going to be a 0, and this ends up to be a 0. So we have 1, 1, 0. And the sign flag is supposed to be a 1 here. So that would not work out. Is that okay, Jonathan? Time was short, but not impossibly short, because some people got it. Some people, got basically perfect scores. Okay, that's okay. All right. Yep. If you think this is not enough time, wait until you start to work for Intel. In industry, they don't really care. They just say, I need this done yesterday, not within the next 80 minutes. Yeah, well, I mean, you guys will see. Okay, when you get out to industry, you will see. Depending on your employer, obviously. If you're your own employer, yeah, maybe things will be a little bit different. But if you work for some of the big names, you can expect your work week to be not just 8 hours a day. That does not exist in the software engineering or development industry. That simply does not exist. Alrighty. So I got this done, and now we can move on to the next topic, which is the fun one, because now we're going to talk about von Neumann. Okay, John von Neumann and his contribution to the computer science, and basically modern computers has to do with von Neumann. It is super duper important to talk about his contribution, because all the architectures that we have today, most are called von Neumann architecture, with a few only called the Harvard architecture. The Harvard architecture can be seen as a derivative of the von Neumann architecture. So we're going to look up John von Neumann. And we're going to look up his Wikipedia page. There we go. And I'm not really sure how many people in this class are curious when they see, oh, we have architectures called the von Neumann architecture. Why is it called the von Neumann architecture? Who is this guy? What did he do? And so on and so forth. I would say probably the majority of people do not care because they don't want to know, because it doesn't really matter. But I want to know. Okay, so that's why we are here on this page. So John von Neumann, or John von Neumann, for the longest time I mispronounced the term, is John von Neumann, because you can see in the pronunciation here the stress or the emphasis is on new. So von Neumann. Okay, there we go. So John von Neumann is an interesting person, because if you look up what he's good at, his expertise, it includes mathematics, functional analysis. I don't even know what this word means. Ergodic theory, group theory, representation theory, operator algebras, geometry, topology, blah 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 blah, and also physics, economics, computing, self-replicating machines. He's way ahead of his time. And stochastic computing, which has to do with probabilistic things. In other words, you're transmitting a signal over a really noisy environment. How do you analyze, and how do you get the signal across when there's a lot of noise? So in every single field that he's in, he's considered the genius in that field by all the other experts in that field. He is that good. Okay. He also participated in the invention of the hydrogen bomb, or fusion fusion bomb. And most people think that he died of cancer because of those experiments. So he got exposed to radioactive stuff when he was experimenting. So he passed away pretty early. He died when he was 53, and the father of computer science, Alan Turing, died before he got to 50. So you can kind of imagine, if these people get to live a little bit longer, computer science, or the way we have computers today, can be very dramatically different or more advanced compared to what we have now. No, we are not talking about the Seinfeld guy. This is a different guy. So now the next question is, you can read about all his history, and he has a very interesting encounter with Albert Einstein too, but that's something that I'm not going to mention in today's lecture. So what is his contribution to computers? So as it turns out, before von Neumann came up with what we now know as the von Neumann architecture, the way you specify the behavior of a computer is by physical wiring. So when you open up one of those really, really old computers before von Neumann, it is the wiring between the components that dictate what a computer should do, how it performs the calculations, and what steps it should be following. In other words, the entire program, okay, what we now know as a program, which specifies the behavior of a computer, the entire program was physical. It was physically specified by the interconnection between the components. Right. So I'm pretty sure you guys are now thinking, wow, so that means if I need to update an app on my phone, I'm going to have to open with the phone, right? Open the case and then unwire a whole bunch of stuff and then rewire a whole bunch of stuff based on the schematic on a piece of paper just to reprogram, just to update, quote unquote, my app. You would be correct. Okay, without the invention that we now know as the von Neumann architecture, that would be what you need to do to quote unquote update an app. And you can probably imagine with the complexity of apps today, even the simplest update is probably going to take you a few days just to unwire and then rewire. And then chances are you're going to make a mistake somewhere and it's not going to work. And then you have to fix it. You have to diagnose the problem, find out what's wrong, fix it, and so on and so forth. So now, getting back to the von Neumann architecture, what was his contribution? It would seem very simple and very kind of like, what is special about that? Okay, by today's standard. What he suggested was simply to store instructions in the memory of a computer. That was his contribution that earned the name of the von Neumann architecture. So before von Neumann, there's memory already, except we only use the memory to remember the data being processed. So if you remember calculus, or if you're taking calculus or numerical analysis right now, the way we compute sine, cosine, log, and that sort of stuff, is in a series, right? So we need variables. We need something to be stored in memory in order to keep track of the sum, so that we can keep adding terms, to that sum. And that requires memory. So memory had existed before his time, before von Neumann made his contribution. Except before that, people never thought about storing instructions. They only store data in the memory of a computer. They never considered storing instructions or what a computer is supposed to do, the behavior of a computer, as a part of the memory. So his contribution seemed small, which is basically just saying, hey, instead of just storing the data that we're processing, let's also go ahead and store the program. Let's also store the instructions in the memory of a computer. It seemed really small, but it was basically an enabled rapid development of software, because now we don't have to physically unwire a whole bunch of connections and rewire a whole bunch of connections and so on. We can now say, okay, once we are done with the hardware of computer, close up the enclosure, stash it in a closet, and everything can now be done using quote unquote a terminal, okay, back in the days of the mainframe. So I'm catching up with the text channel here. Is that a Seinfeld thing on Facebook? Between the two Harvard and von Neumann architecture, what is the biggest differences? Okay, I can briefly mention that because we are not going to get into the Harvard architecture. So the difference between the von Neumann architecture and the Harvard architecture is, in the von Neumann architecture, we use one single memory device logically. It's only one memory device that will both be used to store data and also instructions. So it's used for both. In the Harvard architecture, there are two separate memory spaces. One space is only used for instructions, and then the other space is quote unquote only used for data. So by separating the memory space into these two, now we have doubled the memory bandwidth, and also as a result of that, the side where we are only feeding the instructions can now support very efficient pipelining that was not possible in the von Neumann architecture, where we use one single memory device to store both the data and also the instruction. So the Harvard architecture is basically an enhancement on top of the von Neumann architecture. It is made possible because of semiconductors getting smaller and smaller. So if you look at all the cell phone processors, and if you look into the processor used in Arduinos and also the Raspberry Pi, basically all the smaller embedded small devices, they all use the Harvard architecture in one way or another, because instead of having the memory being a separate chip on the circuit board and taking up space on the circuit board itself. Now they're all integrated into the chip itself, which basically means, hey, there's no need, having the two memory spaces being combined into one, is not useful anymore because they're all on chip. So that is the short explanation of the Harvard architecture versus the von Neumann architecture. Yeah, we do find more Harvard architectures. The only type of computer that still makes use of the von Neumann architecture would be desktop computers and servers too. Servers probably will still be using that model. But when you look at cell phones, when you look at all the embedded devices, your Fitbit device, your iPhone, and your your Apple Watch and stuff like that, I would suspect all of those are now using the Harvard architecture instead of the. I can be wrong, but at least the AVR is the Harvard architecture. All right, so the next topic is going to be, how do we store data on a computer? How do we store something? So, to get to that topic, let me see if I can use my tablet, because it's really helpful to use the tablet even though it's not entirely necessary. And I think my tablet client is still refusing to make that connection. Okay. Let me see if I can get out of the document, get back in, and reset that. There we go. I didn't quite turn it off and turn it back on. I just exited the document and it got back in, and that reset a few things. The problem is I'm running the beta version, as firmware on my Remarkable, so it's not fully debugged yet. So this means I'm gonna have to turn in a bug report after the class. Alrighty. And hopefully the update does not involve me having to unwire a whole bunch of stuff inside my tablet and rewire a whole bunch of stuff on my tablet. Yeah. Beta energy, that's just your fast electrons. Will never hurt you. You will never get cancer because of that, because everything stops at the surface of your skin. Alright, so getting back to here. So I want to show you a circuit. We have two input pins, okay? We have two NAND gates, and that's why I mentioned NAND gates in quote-unquote the past stuff that we have talked about. And then we have two output pins like that, okay? And now we're going to talk about the connection. Yes, I could have done this in Logisim, but there's a very good reason why I did not do this in Logisim. So that reason will be clear in just a little bit. And I'm going to turn off the line in the background because it is not helping. So I'm going to turn the background to just blank at this point. And you would think your blank is easy to find. Alright, grid top, nope. 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 Oh, great. Now it's a music score. I touched something accidentally. I thought about being one, and that didn't work. Apparently, I just have no talent in anything that does not require rational thinking and logic. So I did write a program to self-learn music and quote-unquote compose. That was the last year of my undergraduate study. So I had to give it a whole bunch of melodies to analyze, and it would find out all the common tunes, within all the melodies, and will figure out all the probability of the transitions. So when it comes to the quote-unquote composing phase, it will do a random walk based on the probability of those chunks of common subtunes, of music, and it sounded like, elevator music. It's actually kind of interesting, but I didn't put what is the rhythm into the program, so it was only able to work on melodies. I mean, I worked on it for maybe a few weeks, so it was nothing like what people do now, with neural nets and whatnot. Um, I do not teach algorithms and data structure because I teach just this class: assembly, language programming, and computer architecture and discrete structures. There are other people more qualified to teach those other classes. So I'm proceeding to finish the diagram here. Okay. Oh, I take it back. Okay, this is when I distract myself, things do not work. There we go. All right. So this is one part of the circuit. Is the top input goes to the top NAND gate. The bottom input goes to the bottom NAND gate. But here is the interesting part. Okay, so the output goes here, and the output goes here. Doesn't seem very interesting at this point. However, the output of the bottom NAND gate becomes the input or one of the inputs of the top NAND gate, and the same thing is true the other way around as well. So we tap this. I'm just thinking about how to draw this picture. Okay, we can do it this way. I mean, functional, it is still the same thing. It just looks kind of weird. Okay, so now we have this kind of weird circuit because we have used gates quite a bit. Okay, in fact, we have used fairly complex, gate structures when we talked about the carry look ahead feature, right? Because we have two levels of gates. The first level will be all AND gates. The second level will be a single OR gate. When we talked about the carry look ahead mechanism, but things only go in one direction, which is really kind of easy to analyze. Okay, because okay, we first have to go through this level of gates. When they're done, when they have the right output, all of those outputs will get to the second level of the OR gate, and then the OR gate will do its trick, and then the output of the OR gate is one of the carry bits. But in this case, there's a little bit of a feedback mechanism. Okay, so the question is, how do we analyze something like this? Okay, so that becomes quote unquote the question. So it's helpful to name the components first so that we can actually refer to which input pin, which output pin, and also which gate. Okay, so I'm going to call the input pins just XY for now, and then the output I'll call, okay, I think I might have messed up the names here, but that's okay. As long as I'm self-consistent in this particular lecture, things should still be okay. And then I have to name these two NAND gates. So we'll name these two NAND gates N and M. So here's N, and here is M. All right. So the first thing we want to talk about is the easiest case to analyze. Okay, what if x equals to 0 and y equals to 0? So we want to analyze what's going to happen. So what we are going to do now is we are going to analyze how the change is going to propagate, okay, by looking at the connectivity of the circuitry itself. So we want to find out what is x directly connected to. X is only connected to n. So the next thing that's going to happen, in terms of the propagation of change, is n dot in 0. The top input is labeled 0. The bottom one is labeled 1. Is going to get a 0. And also, we know that y is a 0. That's the change, and it goes into the second input pin or the bottom input pin of m. So now we say m dot in bracket 1 also equals to 0 as a result of that. N dot in input. Yes, it's in for input, and because that's the output too. So, and what's going to happen? Well, after a certain amount of time, we want to see whether this is going to change the output of n, and also we're going to change the output of m. So just happy little accidents. Okay. Um, to me, things are more like Murphy's Law. It's not exactly happy, it's just bound to happen. Anyway, so now we want to analyze the output of n and m. In other words, not knowing what is the second input to n and not knowing what is the first input to m, can we now decide what the gates n and m going to output? So getting back to the problem here. Okay, so given only that we know one of the input pins of n has a 0, one of the input pins of y also has a 0, can we determine the output of the gates that we know as n and m? Well, okay, so this is why I put, okay, let me switch back to the mind map because there are reasons why I mentioned certain things in the mind map. So in the mind map, going all the way back to here, I mentioned NAND gates, right? Negated AND gates. So now getting back here, can someone give me the truth table of a NAND gate or NAND operator? So we got X, we got Y, and then we have X NAND Y, 0, 0, 0, 1, 1, 0, 0, 0. And what would be the values of the column corresponding to the expression of X NAND Y? You can just spell out the values like, oh, I forgot the last row. My bad. 1, 1. There we go. Yep. Nathan is right. Daniel is right. Okay. And Matty is right too. So you guys caught me making that mistake. But now that the mistake is fixed, what do you think would be the values on the column corresponding to X NAND Y? And Richard is the first one. Nice. Okay, so you guys are all correct. Richard, Jonathan, Alexander, and Daniel. I like Daniel's answer. They're all correct. Okay, so it's going to be 1, 1, 1, 0. Okay, so the only time X NAND Y is going to get a 0 is when both inputs are 1s. If at least one input is a 0, X NAND Y is going to output a 1. Right? So that means we have all we need to determine the output of n and m at this point, because both gates, okay, both n and m, each one has at least one input being a 0. And according to the truth table of NAND, if I have at least one input being a 0, the whole thing is going to output a 1. I don't need to care about what the other pin is doing. Okay, the other input pin is doing. So that means in terms of the analysis, now we say, oh, okay, we now know that n dot output is going to be a 1, and we also know that m dot output is going to be a 1, which basically, just as a label, we can now say, output pin A and output pin B are both 1s at this point. But Tech, your circuit has a feedback. This thing can potentially go back and change something because we have a time loop here, right? Someone from the future is now going back in time to change the past. So we can follow the feedback here, okay, going back here, and this one goes all the way back to here, and it's not a problem because guess what? Whatever the output of n and m are going back to try to change the past is not going to be able to change the past because one of the input of n and m are from the input pins, and the input pins are not going to change, not during this analysis. So even though A and B, or the output of n and m, are both determined, it's not going to change anything at this point. But we have to make sure. Okay, so we're going to make sure, and then we say, okay, so this change in return goes back to affect the gates again. So now we say, in addition to in 0, we also know what in 1 is. It's going to be a 1, and same one over here, except this one is going to be going to bracket 0. Okay, but it doesn't change the fact that at least one input pin of the NAND gates is a 0, so it's not going to change the output. So we basically get back to the same conclusion that m.out is a 1, and then m.out is also a 1. And that's a steady state. Okay, now we have reached a steady state because we get back to exactly the same condition that we were in earlier, and as a result, there are no more changes to propagate. So this completes one single analysis of this circuitry. I'm reading the text channel, and Jonathan Wong said, I understand logically how we can determine N and M's output would be 1, but how are A and B initialized before being set by the output? So they're basically, A and B are basically what we call test points. In other words, they are not really a component per se. They're more like contact points on the circuit board. So you can use a multimeter to touch it to find out what this entire node is having as a state and what this entire node is having as a state. So A and B are not really quote-unquote devices. They are kind of instantaneous. As soon as the output of N and M changes, A and B reflects just that. It's just a point where we can probe and go like, hey, what is the output of N? Okay, what is the output of M? That's what A and B are. Okay, very good. So are we good so far with this analysis? All right, so we got some confirmation. All right, and I'm just looking at the time. We got 10 more minutes. I think we can finish the discussion of the this particular memory device. All right, so so now we have something that looks like this. Okay, we have 0 here, 0 here, and through this entire analysis here, we can now determine that this is going to be a 1 and this is going to be a 1. So the propagation time is, coming from, there's a propagation time here. So propagation delay here. Now from here to here, there's no propagation delay because it is connected by a wire. So this is instantaneous. Instantaneous. Looks about right to me. Could be a typo. That's the problem of handwriting, is there's no spell check. And then from here to here, there's no propagation. Well, okay, there's actual propagation delay, but since it's not changing the output, so it is as if there's no propagation delay. But technically speaking, there is a propagation quote-unquote delay to come to the conclusion that the output did not change. So I'm just going to do the really lazy thing and just copy and paste it over here. All right, so that's a good question. Now we're going to move on to the next stage. Okay, so the next stage starts with this. Okay, so we're going to copy this, move on to the next page, and at this time we're going to have a change. Okay, so this is about change propagation. So how do we figure out things as things are changed? So we're going to change one of the input pins. We're going to change, let's say, X from 0 to 1. So let me see how I can kind of highlight the change. I know I can use a thicker stroke. There we go. All right, so we're going to change this one to a 1 here. Okay, so that's the first change. So now the question is, so how do we analyze all of this? Okay, so the first thing is the input X is now changed to a 1. That's the change, initial change. Okay, so this is going to lead to n dot in 0 being a 1. Now this part is instantaneous. Okay, I cannot stand it when I don't know the correct spelling, so I'm gonna go check it, or you guys can check it for me. Instantaneous. That seems correct. Okay. All right, so this one is instantaneous, And then we have, so now what is happening to n? So you have to kind of keep track of what it was, right? So this input was a 1, and let me see, this input was also a 1. So now, at this very moment, both inputs of n are 1s. Okay? So now, after a certain delay, the output of n will become a 0. And I'm going to explain here, because n dot in 0 is a 1, and n dot in 1 is also a 1 at this point. So this one does have a propagation delay. All right. So what that means is the output of n, it used to be a 1, and now it is turned into a 0. And the question is, do n1 is 0 at first? Yes, that's coming from the previous one. So if I go back to the previous page, and this time I have to use a thinner line again, we settle of a and b being 1, but that also means, this is a 1. It also means this is a 1. So that's coming from before. So when we transition to the new page, so initially at least we got 1 going in here, and also we got 1 going in here. But when we change the input pin X from 0 to 1, now n has both input pins being 1s. Alright, so let me read the text channel. I think it's supposed to be a 1 in the brackets. One of them is a 1, the other one is a 0. This one is correct being a 0. This one is correct being a 0. Okay, I'm going to use my mouse pointer because my tablet is not as responsive as I would like. This one is supposed to be a 0 because it is because of X changing. This one is a 1. Oh, okay, bad penmanship. I think it looks like a 2, right? That is supposed to be a 1. Okay, so let me fix my penmanship. There we go. In elementary school, I spent all my recesses, basically practicing my penmanship, my handwriting penmanship. So, obviously that didn't help. All right, so n dot out is now a 0, and what is the result of that? Well, the first one is not really that important. The output A is going to be a 0 at this point. So output pin A is going to now be a 0. Okay, but that's really just a test point, as I said earlier. It's not really that important when it comes to the analysis of the entire circuit. What is more important is where is n dot out going? So n dot out is here, and it goes around, and it goes into M, right? So it becomes, so now this goes to M dot in bracket 0. And that is a change because it used to be a 1, now it is a 0. And this one is instantaneous. Instantaneous. There we go. This one is instantaneous because it's just a conductor, that is connecting the output of N to the top input pin of M. So this one is instantaneous. But now we have to look at M and go like, is M going to change its behavior? So that does have a propagation delay because now we are looking at the change of the input pins, and it does take a little bit of time for a gate to respond to the changes of the input to quote-unquote potentially change the output. So there is a propagational delay in this case. But fortunately, we still have y being a 0, so that means M is still continuing to output a 1. And so let me write that down here. So M dot out is still a 1 because they're both zeros now because both inputs are zeros. Are we good so far? I'm looking at the time because I want to at least get to the point where we have stored the bit. Okay, so right now we haven't really stored the bit yet. In fact, I forgot to change A. A is now a 0. Right? Yes. Okay. All right. So let me correctly reflect the current state here. So this is now a 0. Okay. Very good. So we are gonna copy this again to the next page. We'll do one last change, okay, before the end of today's class. So we got, oh, okay, wrong thing. Let me do it one more time. Copy. No, not here. Let's put it here. And then we want to get rid of this. And then move this up to here. All right, there we go. Okay, so what we want to do now is to change y from a 0 to a 1. Okay, so this is the initial change, which is changing the voltage applied to the input pin of y. That's the initial change. Instantaneously, it's going to change m dot. Oh, okay, it's going to change m dot in 1 because it's connected by wire. Oh, I forgot. Never mind. We're changing it to a 1, so we want to reflect that this is a change from a 0 to a 1. There we go. So now we know this is a 1, and this is still a 0, right? So this is now a 1, and then we have the propagational delay, So because the input of m is in fact changed, because it used to have 0, 0 as its input, now it has 0, 1 as its input. So it does take a little bit of time to determine what the output is going to be. Now, even though the output doesn't really change, there's still a time delay to confirm that the output is not changing. Okay, so there's still a propagation delay in this case, even though when you hook up a scope or when you hook up a multimeter, there's no observable change, but we still know that internal to the circuitry, it takes a little bit of time to determine that the output is not changing in this case. So after a little bit of propagation delay, m dot out is now determined to be a 0. Now you might say, sorry, it's still a 1. It continues to output a 1 in this case, but we can make that confirmation only after the propagation delay. Now, because m dot out was a 1 before, okay, let me go back to the previous slide. M dot out was a 1 already before, and it is continuing to be a 1, except we need that propagation delay to confirm that. But since m dot out is not changing, that stops the propagation. There are no additional changes that we need to track, because now we have gotten to the same point as the previous diagram. There are no additional things to change, to track. So let me summarize. I know we are getting a little bit over time, but let me summarize because this part is important. So if I look at the input XY and I look at the output AB in this particular sequence, we have 0, 0. Okay, so this is not a truth table. Okay, this is not a truth table. I'm simply looking at the sequence of events. So this is sequence lowercase a, which is the first one. We got both outputs being 1s. In sequence B, which is the next step, we change one of them to a 1 first. I think X was changed first to a 1, Y remained as a 0, and we end up with A being a 0 and then B continuing to be a 1. And then we have step C, which is changing Y to a 1 as well. So now we have X being a 1, Y being a 1, and the output are not changed, like so. Our so-called lab today is the beginning of the positive exponent lab or / assignment. You have 1 week to work on it. I mean, you guys can get into it right now and see that the due date is in a week. So you have overlapping, you have two labs basically overlapping, which I think is not really bad at all because the two programs or the two algorithms are very much related. One is kind of the opposite of the other one. So once you get one solved, the other one shouldn't take much time. Yeah. Um, so anyway, we want to remember this sequence of events for now, okay? Because on Thursday, what we'll do is we are going to change B, okay? We'll keep step A, we'll keep step C, but we'll change step B so that we keep X as a 0 and then we change Y to a 1, and then we'll find out what happens in step C as a result. And then we go like, wow, this doesn't mean this does this mean that the truth table is not going to be very useful to look at the current state of this type of circuitry? And the answer is yes, because it is a memory device. It can remember, quote unquote, remember what happened in the past step. Okay, so that's why this is the most elemental, this is the simplest memory device in modern day electronic computers. This is called an SR latch. Okay, SR latch. Sometimes people call it SR flip-flop, but I think the term latch is more appropriate in this case. Alright, so the lab is open and I am done with the lecture today. You probably want to read ahead because the other concepts, the D flip-flops, those are a little bit more involved. So reading ahead should definitely help. It should not have multiple instances of main with the monolithic file. I think that was shared last time. So let me take a look. But I think we are done with the lecture. So I'm going to stop streaming and also screen sharing. Okay, so I don't have it uploaded. Okay, all right. Let me paste it today. Hopefully I saved it in my online GDB. It's still streaming and screen sharing right now, so you guys can see exactly what I'm doing here. Let's see. How do I get to my projects? And we want the one that I just worked on earlier. I believe it is this one. And I want to make sure that this one doesn't have the solution. Nope, doesn't have the solution. And we want it to compile, or at least debug. Alright, so this one does compile, and I'm gonna copy and paste it into the text channel. Give me a second here. Select all, and then I'm gonna paste it here. There we go. That's the entire program copied and pasted into the text channel. Or you can always follow the same steps that I did last week, to get rid of the extra pound includes that are not needed anymore. Yeah, so the only problem with the file that is attached to the assignment is it has all the extra pound includes. So if you get rid of all the extra, if you get rid of all the pound includes with double quotes in it, that should work. So that's another way to, for the project to work. Alright, so I hope that addresses all the issues. Let me see if there are any new comments in the text channel. Nope, I'm not seeing anything. Alright, so I'm gonna stop streaming and